Welcome to the deep dive. We're looking at some research today that tackles, well, a really common headache in high-performance computing. It's all about getting engineering software, specifically these parallel finite element method programs, to actually run fast on modern multi-core processors.
Right.
For years, the deal was simple. More cores meant more speed, pretty much. That was the old SMP symmetric multiprocessing world. But now, we've got chips with dozens, maybe hundreds of cores, and that nice simple performance curve kind of falling apart. So this deep dive is about figuring out why and what developers really need to watch out for now.
Exactly. And our mission today really is to cut through some of the noise around these ccNUMA architectures. That's Cache-Coherent Non-Uniform Memory Access. They're everywhere in modern servers, but they bring this big challenge, the idea of shared memory, where everything looks the same to every core. It's starting to fray. You might think all memory is created equal for every core, but physically, no, not at all.
And the research kicks off with a failure that just perfectly highlights this, like really starkly. Researchers took this FEM code, right, designed to be super efficient, scaled great on older 8-core SMP machines. They put the same code, didn't change a thing, onto a modern 64-core ccNUMA system. Expected a huge boost. Instead, they got a speed up of only 2.8 times using 64 threads. That's almost nothing compared to what you'd hope for, like a 95% drop from perfect scaling.
Yeah, it's a real wake-up call for anyone working on performance. The issue is right there in the name, non-uniform. Yeah. See, in ccNUMA, memory banks are physically closer to certain groups of cores called nodes. Sure, every core can access all the memory technically, but if your core needs data that's physically attached to a different node, well, that request has to travel across an interconnect, and that adds delay, latency, measurable latency. It's much slower than grabbing data from its own local memory bank, and if you ignore that physical layout...
Yeah, the system performance tanks. Okay, let's unpack that 2.8x slowdown. The code for this test case was highly parallel. It broke down these big matrices, replicated them. No need for locks or syncing between threads. So if it's not waiting on other threads, how could the processors possibly be idle for so much of the time? What did the diagnostics actually show?
Well, they immediately went low level, used tools like perf on Linux to see what the processor cores were actually doing. And the numbers were pretty startling. The application wasn't just slow, it was almost stopped. It was only executing an average of 0.05 instructions per cycle.
IPC. 0.05 instructions per cycle. Just to give some context, modern CPUs are built to run multiple instructions every single clock tick. 2, 3, maybe 4 or more. An IPC of 0.05 is it's like having a race car that spends almost all its time sitting at a stoplight. The engine's running, but nothing's happening.
Exactly, but that's a great analogy. And the next question was, why wasn't anything happening? The key metric turned out to be stall time. The processor's backend, that's the part that actually schedules and runs the instructions, it was stalled 59.7% of the time. Just think about that. Almost 60% of the total clock cycles, which is like 6.6 trillion cycles in their test, just lost, waiting.
So the processor's just sitting there waiting for work. And you said that stalling was traced back to cache misses filling up the load store queue. Can you break down what that queue, the LD queue, actually is and why filling it is so bad?
Sure. Think of the load store queue, the LD queue, as the processor's little waiting room for memory stuff. Reads or writes. When a core needs data, the request goes in the LD queue. The data is right there in the L1 or L2 cache. Super fast. The request is handled, space frees up. Easy. But if the data has to come from main memory, and that memory is physically far away on a remote main node, well, that takes a long, long time. That request just sits in the LD queue, could be hundreds, maybe thousands of cycles waiting for the data to make the round trip. Now imagine you have 64 threads all hitting these slow remote memory accesses at the same time. That queue, it fills up instantly. And when the LD queue is full, the processor literally cannot issue any new instructions that need memory access, even if other parts of the core are free. So that's the chain reaction. Remote memory access causes high latency fills the LD queue. A full LD queue stalls the CPU for, 60% of the time in this case. That was the core problem.
Okay, but here's the part that feels weird. My first thought, and probably yours listening, is memory misses are the problem, so the caches must be the issue, right? Maybe they're too small. But the research says the L1, L2, even L3 cache misses barely went up, like maybe 3 or 4% more misses when they went from 1 to 64 threads. That small increase doesn't seem to explain this total performance collapse.
It doesn't, you're right. And that's when you realize, okay, the problem isn't really the application code itself or even the cache sizes. The problem is the interaction between the application and how the operating system manages memory on this specific ccNUMA hardware. The key finding, the aha moment, was realizing the test setup used the standard Linux memory policy. First touch.
First touch,
Right.
which normally sounds like a good optimization, but here it backfired spectacularly. Why?
Yeah, exactly. First touch means the physical memory page gets allocated on the NUMA node that's closest to the core that first writes to that memory. Now remember how the test worked. The main thread set up and replicated all 64 of those big 46 millibit matrices before the parallel work started. So guess where all 64 matrices ended up? Physically allocated on the memory bank closest to wherever that main thread happened to be running. On their test system, that was node 3.
Oh, wow. So they had 64 cores spread across, what, 8 memory banks?
Mm-hmm.
But because of this default OS setting, all 64 parallel threads were trying to hammer the one memory bank attached to node 3. It's like having 8 checkouts open at the store, but the manager makes everyone line up at just one of them, register 3.
Perfect analogy. That's exactly it. Cores that were physically far from node 3 had to send their memory requests over that slower interconnect bus. That generated all those huge latencies, filled up the LD queue, and led straight to that miserable 2.8x speedup. The application logic was parallel, sure, but the memory access was totally serialized at node 3.
Right. So the good news, maybe, is if the OS policy caused the mess, maybe an OS policy can fix it, and the first fix they tried didn't require changing the FEM code at all, did it? They just used a tool, numactl, to switch the memory policy to interleave.
Exactly. Interleave is kind of the sledgehammer approach. Instead of letting everything pile up on node 3 based on first touch, this policy tells the OS just spread the memory pages out evenly. Use all the memory banks node 1 or 2, node 3, etc. in a simple round-robin fashion. Page 1 in node 1, page 2 to node 2, and so on. And the result, bam, immediate huge improvement. Just physically spreading the data across the 8 banks allowed the memory accesses to happen in parallel too. The speed up jumped right from that 2.8x all the way to 10.6x.
Wow, 10.6x,
Yeah.
just by telling the OS to spread the data out. That single change, no code edits, proved that memory placement was, like, the vast majority of the issue, right? It accounts for maybe 80% of the lost performance right there.
Absolutely. It clearly showed the bottleneck. But interleave isn't perfect either. It's still kind of a blunt instrument. Because it spreads pages of memory across all banks, even a single thread working on its own dedicated matrix ends up having its data scattered. So every thread is still likely accessing multiple memory banks, including ones that are remote, just not all hitting the same remote bank simultaneously. You solved the massive contention, but you haven't really optimized for data locality. Plus, the OS could still decide to move a thread away from the cores nearest its data later on.
Okay, so to get closer to that ideal linear scaling, they knew they needed more precise control. Control over both where the data lives and where the threads run. And that meant actually modifying the application using special libraries.
Right. They turned to libNUMA. It's a library that lets developers basically bypass some of the OS's automatic stuff and manually control core affinity and memory placement. And they did 2 very specific things to try and achieve perfect locality.
First step was careful allocation.
Yes, cautious allocation. Using libNUMA, they explicitly placed each of the 64 matrices onto specific memory banks in that round-robin way. Matrix 1 on bank 1, matrix 2 on bank 2, matrix 9 back on bank 1, and so on. So each bank held data for 8 matrices. Then, the second crucial part, thread scheduling. They used libNUMA again to pin or constrain each computing thread to run only on the cores physically located right next to the memory bank holding that thread's specific matrix.
So forcing perfect alignment. Thread runs here, its data lives right next door.
Exactly, creating perfect local affinity. And the results were, well, pretty spectacular. This approach, which is highly manual and definitely not portable, pushed the performance up to 30.9x speedup on 64 cores, which really demonstrates the potential. If you manage everything just right on ccNUMA, you can get very good scaling.
Okay, 30.9x. That's impressive. It shows the hardware can do it if you wrestle with it enough. But doesn't that kind of suggest the default OS scheduler is, well, maybe not up to the job for these big parallel systems? Why should software developers have to use these specialized libraries like libNUMA just to get decent performance?
It's a fair question, philosophically. But the practical answer is that operating systems have to be generalists, right? They don't know the specific memory access patterns of every possible application, especially something complex like FEM code. And the big drawback, the reason you don't want to rely on libNUMA for production code, is portability. It's basically Linux only. If your company needs this NeoPZ library to run on Windows or maybe some other specialized Unix systems, that 30.9x solution, it's a dead end. You can't use it.
Right. Which leads us to the third approach, the one proposed as the practical solution. It aims for that high performance without sacrificing portability. This is the copy-on-thread idea.
Yeah, this one's quite clever, actually. It sort of uses the OS's own default behavior, that problematic first-touch policy against itself, but in a good way.
Yeah.
The core idea is pretty simple. Don't let the main thread allocate all the data up front.
Instead, the thread that's actually going to do the work on a particular matrix is responsible for getting its own copy.
Exactly. Before the real number crunching starts, the worker thread assigned to, say, matrix 5 first allocates a new chunk of memory and then copies the original matrix 5 data into that new space.
Ah, I see. So by having the worker thread do the allocation and the first write the copy operation, it leverages the OS's default first touch policy to automatically place that new copy of the matrix data onto the memory bank that's physically local to the core where that worker thread is currently running.
Precisely. It basically tricks the OS into creating data locality for you without needing any non-portable libnuma calls. It's all done with standard memory allocation and copying.
That is smart. But wait, you're copying these big matrices, 46 megabytes each, 64 times?
Yeah.
That sounds like a lot of overhead, just moving data around before you even start the real computation. And like you said before, even if you get the data local initially, the OS might still move the thread later, right?
True, the copy isn't free, that's the trade-off. But the researchers found it was absolutely worth it. This copy-on-thread approach, it achieved a speedup of 25.5x. Now, that's not the absolute peak of 30.9x they got with manual control, but look at it this way. It's nearly 2.5 times better than just using the simple OS interleave setting. And, crucially, it gets you that great scaling using only standard portable code. No Linux-specific hacks.
Okay, so for something complex like the NeoPZ library, which needs to run potentially anywhere, this copy-on-thread looks like the winner, doesn't it? It gets you, what, maybe 80–85% of the absolute best possible performance, but maintains that critical portability for real-world use. You trade a little peak speed for a lot of flexibility.
That seems to be the conclusion, yes. But there's a really important piece of context here. When do these NUMA memory issues really bite you? The authors were very clear. This huge bottleneck, the drop from expected scaling down to 2.8x, it only happens for large data sets, like those 46 milbase matrices they replicated.
Right, and that's a critical caveat we need to mention. They also ran tests with a much smaller matrix, only 615 kilobytes. In that case, 2 copies of the matrix could easily fit inside the local L2 cache of the cores. So the main memory bottleneck, the whole ccNUMA latency problem, it just disappeared. And for that small data scenario, the overhead of doing the copy on thread actually made it slower than just using the default first touch policy.
Which just goes to show optimization is never one size fits all, is it? You really have to know your data. If your working set fits in cache, adding copy overhead is just wasteful. If your data is large and lives in main memory, then managing locality becomes absolutely paramount.
And they did test this on the real FEM problem from the sources, right? The one with 200 substructures over 150,000 equations.
It did, yeah. And the results held up. The simple OS interleave policy gave about 8.8x speedup, but the portable copy-on-thread strategy reached 17.3x speedup with 64 threads on that real-world problem. So the principle definitely applies outside the synthetic test case.
So that whole journey, from that dismal 2.8x starting point up to 17.3x in practice, or even hitting 30.9x in the lab, it really drives home the point. On modern multi-core systems, memory organization is the new frontier, the hidden bottleneck. You just can't treat memory like one big uniform swimming pool anymore, even if the programming model looks like shared memory. You have to think about those distributed banks.
Absolutely. And connecting it back to the engineering domain, FEM specifically, the authors mention another way you might try to sidestep this whole memory issue. Instead of dealing with large substructures that spill out of cache, you could change how you decompose the problem in the first place. You could split the original simulation mesh into many, many more, much smaller substructures.
Ah, so the idea is if each substructure is tiny enough, its data will fit entirely within the fast local cache L1 or L2 of the core working on it.
Exactly. If you can keep the working data cache resident, you completely avoid those slow cross-node ccNUMA accesses to main memory. Problem solved in a way.
That sounds like the dream scenario for performance, maybe. But you mentioned there's always a trade-off.
Right. Making hundreds or thousands of tiny substructures gives you great data locality and potentially massive parallelism. But it can also make the overall mathematical problem harder to solve. The solver algorithm might need many more iterations to converge to the final answer when the problem is broken down that finally.
So that leaves us with a really interesting final thought for you, the listener, especially if you work in this area. How do you balance that fundamental trade-off? Do you push for extreme parallelism by creating tons of tiny substructures, hoping the faster memory access outweighs any extra solver work? Or do you stick with larger data structures and rely on clever, portable memory management tricks like copy on thread, accepting their overhead, finding that sweet spot? Well, that's the ongoing challenge in optimizing complex engineering software today.